did, and print them all out to know if you have a linear graph. Have you done this in statistics? Anybody have statistics? Nathan?
We do this a lot.
You do what?
We do this a lot.
Okay, good. So what do we use?
R value.
You use the R value. Yeah. You ever heard of R value? Do you have to be in stats to do that? No, you don't have to be in stats? Okay, so you're familiar with R squared, the linear regression.
What?
Lots of answer.
This is great. Watch this. I'm right-clicking on one of the data points, and I want to go to Add Trendline. See that there in the menu? Add Trendline. So it'll tell us the equation for the line. I'm clicking on that. I'm going to get a menu that shows up. And at the bottom of the menu, there's two things we want to... Oh, look at that bottom one. Display the R-squared value. We want that. So click on that. And then the second, the bottom one, display the equation on the chart. That's going to be nice too. So the people that make Excel, though, why do you have to put it right through the line? Yeah. They didn't ask us. And we can still read it, though. So for this one, we have an R-squared value of 0.9852. How do you feel about that? Pretty. What do we want the R-squared value to be if it's perfectly straight?
1.
Yeah, it'll be 1. Do you think you're going to get a perfectly straight line when you do the lab?
Nope.
Yeah.
No, I'm pretty sure you won't. But you'll get pretty close to 1, I think, for one of them. Do the same thing with this graph, too. We don't need to do it for that because we can see the eye test tells us that one is definitely not straight. So I'm going to go to Add Trendline on my second order, do the same thing, give me the equation and the R-squared value. And I knew you'd be surprised. The second order one is more linear. You had no idea, did you?
No, I didn't.
I knew. So anyway, yeah, the R-squared on the second order is 0.9995. It's very linear.
Oh,
Yep. You were close on that one. So we know this is a second order reaction. That means we can write the integrated rate law. And if I can go back now to the presentation, here it is. So let's see. The integrated rate law. Because we know that it's second order, we could say this. Remember, second order is the inverse of C4H6 equals KT plus 1 over C4H6, 0. That would be the integrated rate law. And we know it's got that form because that's the form of a second order, which was the straightest of the three lines. Yeah?
So to solve these problems at home, you should have to graph all of them and then find the R.
the butt.
Yeah.
Just do a couple. Because if you can do a couple and get comfortable with it, you got it.
Graphing calculator.
Yeah, for sure, if you have a graphing calculator. Some people just whip them out really fast in their calculator. I don't know how to do it.
It's really easy.
Good.
Wow.
I would love that.
Graph and
Yeah.
find R on the calculator.
I think it'll tell you. It'll do the regression for you.
Statistics.
Check the statistics, Ben.
Linear regression.
Now it also asks us, can I have you look up here again? Because I know you're looking at your computers. Your calculators.
Computers.
I'm at your calculator. It says, find the rate law, the integrated rate law, and find the value of the rate constant for this reaction. The computer already told us what the rate constant was. If I can go, let's see, what do I have to do here? I go back to my Excel. Yeah, the K value is right there. 0.0, can you read it? 0.0142x. That gives us the slope of the line. So that is the rate constant. That's the K value for this thing. Now, does that mean it's a fast reaction or slow? We don't really have anything to compare it to, do we? And what would the unit be? We always have to give the unit on K. Yeah, T is, in this case, in seconds. It was the temperature is measured in seconds. Let's think about it. The unit on this one is interesting. We're graphing 1 over the concentration. And the denominator. The x-axis here is in seconds. So when we find the slope, what's the unit of the slope? That's K, K's unit.
1 over
So it's like seconds over time, concentration.
Concentration. Wait, what?
Not really. It's y over x. So the y is 1 over molarity, and the x is seconds. So it's 1 over molarity over seconds,
Yeah.
which is this thing right here. So when it's a second order reaction, the unit on K will be 1 over molarity seconds. It's a strange unit. It doesn't really have physical meaning. You could also say in the solutions manual will tell you it's liters over moles seconds. Because you know how molarity is moles per liter. So the inverse of molarity would be liters over moles. You'll see that too. If it were a straight line for the natural log graph, it would be a first order. What would the unit on K be then? It wouldn't be the same. With this one, we're taking the natural log of the concentration. When you take the natural log or the log, it goes without a unit. There's no unit on the y-axis on this one. I'll say that again. Anytime you take the log or the natural log, you wind up with no unit. It's just a numerical analysis. So I'm going to say it again, the denominator. The x-axis is in seconds. So if it was first order, the unit on K would just be 1 over seconds. We'll deal a lot with that. Yeah.
How would you go like this in your calculator?
What?
How would you like do this in your calculator? Like,
Oh, I don't have any idea. I told everybody yesterday I don't know how to do it on the calculator.
You did not.
I'd do it by hand if I had to use a calculator because I don't know how to do it. But people tell me that it's easy. So you have to have a
how would you
quick...
do it by hand?
Take a piece of graph paper and find the natural log of all these and plot the points. And hope that one of them looks more straight than the others. Hold a ruler up to it, I guess. I don't know.
Something what? I'm so confused.
All right, so we can't spend our class time doing that. I'm going to run out real fast if we get into how to use a calculator. But yeah, find somebody that can show you how to do it. Maybe go order them a Starbucks and have them show you how to graph in a calculator. So if you're one of those that's knowledgeable in the calculator, don't give your knowledge away for free. Yeah, at least get a coffee out
I
of
get
it,
it. Yeah.
right? Yeah, a frappuccino or something.
I just showed you.
Yeah. He owes you.
Yeah. Interesting.
YouTube.
Yeah, there is YouTube. Yeah. Okay, so that's pretty much what we're going to have to do to find the integrated rate law. Is it difficult? No. Is it tedious? Well, yeah, it can be tedious because you have to plot 3 different graphs. But when you have the use of a calculator, it is much more handy than graphing by hand, isn't it? All right, so that was where we were. Yeah, we do need to talk for a few minutes about half-life. When we do the lab on Monday, I will ask you what the half-life of the reaction is. The half-life is also going to depend on the order. We learned about half-life back when we did Chem 1 nuclear chemistry, like how radioactive something is measured by its half-life. We can also find the half-life of a reaction. If a reaction has a very short half-life, what does that mean about it?
Very
You said unstable. You're still thinking nuclear changes. Yeah. Something that's radioactive has got a short half-life. It's going to decay fast. So if you have a reaction with a short half-life, what does that mean?
very fast.
It's a fast reaction. Take a look at the definition. Half-life is the amount of time that it takes for the reactant concentration to get cut by half. So if it doesn't take long to cut the reactant concentration in half, that means it's a fast reaction. Thank you, Jane. You gave us a warning that time, didn't you?
You heard it?
I heard something. I didn't know.
I was like,
Yeah, I saw it.
Yeah,
That was nice.
the warning's gonna be like. It's gonna be like dying.
And if you're not watching, too bad. Okay. So yeah, half-life is an amount of time. Half-life will always be measured in the time unit given in the problem. Most of the time it's in seconds, but watch out, sometimes it'll be in minutes. So just be aware of that.
Could be hours.
Possible, but I don't think you're going to see any of that.
it's years.
What about
Yeah,
those
some reactions take years.
Millions of
man-made like elements, like 100?
What about them?
Are those like really like those are really
Short half-lives.
years.
Yeah.
Like,
Some of them are less than a second,
yeah. Like
a
100.
millisecond.
Yeah.
for instance. Yeah, I mean, they're very unstable. Okay, I'm going to derive what the half-life equation is for a first order, and then if it's all right with you, I'll just derive the other two, I'll just give you. Here's how we derive it. Now, I'm going to be honest with you. If you come up and ask me a half-life question from your homework, I'm not going to know off the top of my head what the half-life equations are. I get confused. I forget them constantly and mix them up. I can remember the first order half-life, but the 0 and second order, I'll derive them every time. So it's not going to take me long, but I do want you to know it is possible to not have to memorize these things. And I personally prefer not to. I'd rather just figure it out as I go, because I know I can figure it out better than I memorize. So this is the key right here, this thing. At the half-life, that means that whatever your reactant was at the beginning, it gets cut in half. So A's concentration is half of what it was at the beginning. That's what your reactant concentration is at the half-life. And so the question is, we're going to try to figure out that thing right there. You got to solve for T. How long does that take for A to become half of A0? So let's plug in. The natural log of A, if we're at the half-life, A is the same thing as 1/2 A0. So that means this. ln of 1/2 A0 equals negative KT plus ln of A0. And we're solving again for that thing right there. We want to try to get that by itself. Okay, well, what do you want to do? Should we take that ln of A0 and move it over if we're trying to solve for the T? Yeah, let's do that. And then when we do that, ln 1/2 A0 minus ln of A0 equals negative KT. We're solving for the time. Is there anything you want to do with the left side?
We can do ln of.
Yes, we can use the properties of logs. And if we have ln of something minus ln of something, that's the same thing as ln of that divided by that. Shall we? That'll be fun. Come on. ln of 1/2 A0 over A0. There we go. Equals negative KT. I want to try to extend the page. I don't know why it's not letting me. Usually there's a little blue thing down there that says extend or expand page. I don't know why it's not letting me. Oh. Don't laugh, Amber. You want to do anything with it now?
Can we cancel the?
Cancel the A0s out. Yeah. Okay. Told you it would be fun. So now we have ln of 1/2 equals negative KT. We're getting close. Anything you want to do with the 1/2 inside the ln? Oh, I know what we can do. We can now expand it back to what it was before. How about ln of 1 minus ln of 2? Why would I do that? You'll see. So let's go right over here and say this. ln of 1 minus ln of 2 equals negative KT. Why did I do that? Nabil? Yeah, ln of 1 is 0. Right. E to what power equals 0? I said that wrong. E to what power equals 1? I gave away. Yeah. So this thing right there is 0. So e to what power equals 1? It would be the 0 power. So now what are we down to? Remember, we're trying to solve for t. I've been doing all this log stuff. And we're down to this. Negative ln of 2 equals negative KT. So solve for t. T equals ln of 2 over k. This is the half-life. Only for first order.